Have you ever stopped to wonder how an email you send from New York finds its way to a server in Tokyo in like a fraction of a second? The magic behind that is a protocol that acts as the Internet's global postal service, BGP. So today, let's break down this invisible force that literally holds the modern Internet together. So here's what we've got on tap. We're going to start with the absolute basics. What even is BGP? Then we'll look at how it works inside a big network versus between different networks. We'll even learn the language that BGP routers use to talk to each other before walking through the step-by-step process of how they connect, and, maybe most importantly, why they sometimes fail to. All right, let's dive right in. Now, before we can really appreciate the solution, which is BGP, you've got to wrap your head around the absolutely mind-boggling scale of the problem it's solving every single second of every day. I mean, just think about it for a second. We're talking about thousands of completely separate networks, all run by different companies and organizations. How in the world does one tiny packet of data find the best possible path from your device through all that chaos to a server halfway across the globe? There has to be some kind of master map, right? Well, that map is BGP. It stands for Border Gateway Protocol, and it's built for one thing above all else: inter-AS communication. That's just a fancy way of saying it gets all those thousands of independent networks to talk to each other. And here's the really cool part. It doesn't just find any path. It helps network operators find the best path based on all sorts of things like company policies, cost, and of course, speed. Let's peek under the hood a little bit. BGP is an open standard, which is a huge reason why it's so universal. It communicates over TCP port 179, and fun fact, that actually makes it an application layer protocol, just like the web browser you're using right now. But here's the kicker. These connections don't just happen automatically. Engineers have to manually configure two routers to become neighbors, and they can even lock that connection down with authentication to make sure they're talking to the right device. Okay, so we know BGP connects different networks, but here's where it gets interesting. It's also used inside a single massive network. And this brings us to a really crucial distinction between what we call internal and external BGP neighbors. To really get this difference, you first have to understand the idea of an autonomous system, or an AS. The easiest way to think about an AS is as a single digital kingdom, like the entire network owned by a huge provider like Comcast or a tech giant like Google. It's a massive collection of routers all under one single management. And this slide lays out the two flavors of BGP perfectly. When your kingdom is connecting to a totally different kingdom, that's eBGP, or external BGP. But when you're just trying to organize all the routes inside your own huge kingdom, that's iBGP, or internal BGP. And check out that administrative distance. Think of it like a trust score. The lower the number, the better. A route learned from an outside neighbor is considered way more reliable by default than one you just heard about from inside your own network. So every kingdom on the public internet needs a unique address, and that's its public AS number. But just like with private IP addresses that you use at home, there's also a private range for AS numbers. You can use these inside your own network for testing or for your iBGP setups without having to ask for permission from anyone. It's like your own private sandbox. Okay, so we know what BGP is and the different ways it's used, but how do these routers actually, talk to each other? Well, their entire conversation, their whole language, is built on just 4 fundamental types of messages. It all kicks off with an open message. That's the initial handshake, the hello. Once they're connected, they start sending update messages. This is the good stuff, the actual maps to different internet destinations. Now, to make sure the line hasn't gone dead, they send a simple keep alive message every 60 seconds. Just a little, you still there? And if anything goes wrong, a configuration mismatch, a bad password, a notification message is sent and the connection is immediately torn down. It's a really simple but super effective system. Now, that connection isn't instant. You can't just flip a switch. Forming a BGP neighborship is actually a very formal, multi-stage process. A router has to move through several distinct states before it's actually ready to start sharing routes with its neighbor. It all begins in the idle state. From there, it moves into connect as it tries to build that basic TCP link. Once that's up, it sends its opening proposal and enters the open sent state. When it gets a reply from its neighbor, it moves to open confirm. And only after both sides have checked each other's proposals and agree on the terms is the connection finally established. This is the golden state. This is when the real work of exchanging internet routes can actually begin. Of course, as any network engineer will tell you with a sigh, things don't always go according to plan. When a BGP connection gets stuck in one of those early states and just refuses to reach established, it's almost always because of one of a handful of common and often surprisingly simple configuration mistakes. So here's the mental checklist that pretty much every network engineer runs through. First, the absolute basics. Can the routers even ping each other? It sounds obvious, but you'd be shocked. Next, you gotta triple check the config. Is the neighbor's IP address and their AS number typed in exactly right? If you're using authentication, do the passwords match character for character? And finally, is there a sneaky firewall somewhere in the middle blocking that all-important TCP port 179? Honestly, running through just these simple checks will solve 99% of BGP peering problems.
So we've seen that BGP is this incredibly powerful, super scalable protocol, but it's fundamentally a manual and trust-based system. It was really built for a different, smaller, more trusting era of the internet. And this leaves us with a really critical question to think about. As the absolute core routing protocol of the internet, how can BGP evolve to meet the incredibly complex security demands of the modern